So the end of the last video, we were just finishing up this problem, and we talked about how the cheapest path was to go from Seattle to LA, and then to Chicago, to Atlanta, to Dallas, and then back to Seattle. And so, if they ask for the circuit, we would put in the letters. If they asked for the price, then we would add up the prices over to the side. So we would add all these numbers up. So just make sure you pay attention to the problem. Is it asking for the lowest cost, or is it just asking which order do I need to travel in? As we look at the first algorithm that we're going to talk about, the first algorithm is called the nearest neighbor algorithm, which is basically what we just did. We select a starting point, which they will give us, and then we move to the nearest unvisited vertex with the smallest weight. And then we repeat it until it's complete. And so usually what I do is I just draw my dots from where they are. So you'll notice that we have 5 dots. And it tells us that we're going to start at the far right. So our furthest right dot is this one or this one. Those are the ones that coincide with each other. And so what we want to do then is we look from that dot, the dot on the furthest right, and we look to see which one's shortest. So we have either 8, 6, 13, or 12. And so our shortest is to go to 6. And so we're going to go across to the 6th one. And from there, so once I get to this one, then I look to see what's the shortest. And so from this one, I either have 14, 11, or 4. Those are my 3 that I could go to. And so I'm going to go to the 4 because that's my next shortest, which brings me to this dot. And so from that dot, we're going to either go to 7, we could go to 9, or we could go to 8. And so our shortest is 7, which is going to be to here. And then once we get to that dot, we're down here. And so from this dot, the only place we haven't been yet is this dot over here. And so that is the 5. And so we're going to go to here and then go back to our starting amount. And so that would be the circuit that we make if we were going to go or use the nearest neighbor algorithm. And so again, we start where it tells us to. They'll always tell us where we're going to start. And then we just go shortest distance until we make a circuit, which means we visit every dot without visiting it more than once. So you can only have 2 lines coming off of each dot. So as we look at the next example, they give us our little picture, and they said, consider the graph. We're going to use nearest neighbor, so that's the NNA, and they want us to start at vertex A. So we're going to start at vertex A. Our choices are either 4 and go to B, 1 and go to D, or 2 and go to C. So we want to go to D. So we're going to go to D. So we're going to go from A to D. From D, we either can go 9 to B or 8 to C. And so we're going to go 8 to C. And then from C, we're going to go to the only other place we haven't been yet, which is B. And then we have to go back. And so then we go back to A. And so we always want to start and end in the same spot. And that's our nearest neighbor for this problem. All right, so looking at example 7, it talks about doing repeated nearest neighbor. And so we know it's repeated because we have an R, and basically we do the same thing starting at each vertex until we figure out which one's the cheapest, and then that's our solution. This one I hate. They will never ask you to do this one on an exam because it takes so long, but on your exercises and on your test or quiz, you will have to do it. And I just apologize right now. So we started with A, which we just did. And so if I do A, I go to D, which is 1 space, and then I went to C, which was 8 spaces, and then I went to B, which was 13, and then back to A, which was 4. And so that's my first path. And so then I add those all up. So we have 9, 14, 13. So we have 26. And then we're going to do the same thing, but starting with B. So if I start at B, my shortest path is going to be 4, 9, 13. So my shortest path is going to go to A, which is 4. From A, it's going to go to D, which is 1. So we're going to go A to D, which is 1. And then we have to go to C, which is 8. And then back to B, which is 13. And so again, we add those together. So we have 5, 13, 13. So we have 26. And then we do it again, exactly the same thing, but this time we start with letter C. And from C, we either go 2, 8, or 13. So we're going to go 2 up to A. So we're going to go C to A, which is 2. And then from A to D, which is 1. And then from D to B, because that's the only place we can go. And then back from B to C, which is 13. So again, we're going to add those together. So we have 2 plus 1, 3, 9, 12, plus 13, 25. And then we have one last way that we need to go, which is starting at letter D. And so we're going to go from D. We have either 8, 9, or 1. So we're going to go up to 1, or up to A, which is 1. And then from A, we either can go 2 or 4. So 2 is shorter. And then we have to go to B because we haven't been there yet. And then we go back up to A, which is 4. And again, we add them together. So D to A was 1, A to C is 2, C to B is 13, and B to A is 4. And so if we add them together, we get 20. And so our shortest path is starting with letter D, and the cost would be 20. Now, usually what happens is once you get to that point, then they ask you to write the circuit starting with a specific letter. And so that's where we usually run into problems, because you have to do this process in order to get which circuit is the shortest. But when you put it in the computer, they'll make you rewrite the circuit. So if I'm saying this circuit is my shortest, I would rewrite it starting with letter A. And so I would say it's A, C, B, D, back to A. And so this would be the circuit that I would enter into my computer. But it's really it's really the winning circuit is just rewriting the winning circuit starting with letter A and then going to the left and back around. So just be careful with that. Using the table, you can do it the same way. I could go through all of it, and I will slowly, but I don't want to. You'll be bored out of your mind if we do every single problem. But again, as we look at this, the nearest neighbor, if I'm looking at doing it from a table, so example 8 has you do this from the table. So it says using nearest neighbor, starting at vertex A. So I'm starting at vertex A, and so I can either look down or I can look across because your values are the same. So it doesn't matter. So from A, I want to figure out where am I going to go that's the easiest to get to, with the shortest route, I should say. So as I look down the A column, the shortest value is E. So I'm going to go to A to E, and then from E, I look down the E column, and the shortest path is 15. So shortest path was 8. Then I go to the E row or column, and I get 15, which is C. And then I look at this C row or column. I'm just going to look at the row. And the row, the shortest is 5, which is D. And then I look at the D column, and the shortest path is F, which is 6. And then I've gone everywhere except for B. So I don't really have a choice. The only place that I don't have something marked is column B, right? Because I have E marked, I have C marked, So anyway, I have these values that have already either have a circle or an X in them, depending on which way you're going. And so when you look at it, we have F marked as well. And so the only column or row that doesn't have something is B. And so that means I have to go to B. We haven't made it to B yet. And so from F to B, the only value that I have left, or the only place I can go, is 24. And then I have to go back to A because I always have to make a circuit. And so from B, I have to go back to A. And so this would be the list of vertices starting and ending with vertex A. So starting and ending with vertex A, making sure that I visited everybody. I can do that a couple different ways. That's one option. Another option is I can just make, like if I make myself a chart to help me do it, I know that I'm starting at point A. I'm looking to see where am I going to go. So you can still do it the same way and just draw yourself your own mapping and say from A, the shortest path is to go to E. And then from E, your shortest path is go to F. And so it just kind of helps you stay organized. From F, your shortest path is 6, which is D. It also makes sure that you keep track of only 2 points coming off of each line. From D, our shortest path is to C. And the only place you can see that we haven't been to yet is B. And so they're going to close our circuit up. And so you can also do it that way and then write your circuit starting with A. Either one works. The same thing applies if I do repeated nearest neighbor. And this is what I was saying is if I do repeated nearest neighbor, I have to add those values together and find out the cost of each one. But I do the same process over and over and over again until I get my values. So we just did A up above, and these are the values to go from each number. So each vertex to the next vertex, that's how I'm getting these values. And then I would total all of those together, and that's how I get my total. So I would just add all the numbers together and find out which one is the cheapest. And that's how I know which one is going to be the winner. Now, the problem again with repeated nearest neighbor is that you have to do this, in this case, 6 times in order to figure out which one is the best option. And then once you have the cheapest option, then you have to figure out or you have to write it starting with whatever letter they tell you to. And again, you would just add those numbers up, find out what the cheapest is, and then go from there. That's going to take forever. Hopefully, if it was me and you're watching this, I would try to make sure that you understand how I'm getting those numbers and go from there instead of us spending another 10, 15 minutes trying to create this. And that's why I said they'll never make you do this on exam because it takes so much time. The next algorithm is called sorted edges or the cheapest link algorithm. And the nice thing about this is it's very similar in the fact that you're trying to do cheapest, but you get to just go the cheapest route, cheapest route, cheapest route until you create a circuit instead of them telling you where to start. So if I look at example 10, I just look at my picture and I say, well, the cheapest route is here. My next cheapest route is here. The next cheapest route is 4, but I already have 2 lines coming off of A, so A is now done. The next cheapest route is 8, but that would close my circuit without getting or making it to B. And so I really have no other choice. The next cheapest route is to B. And then I have to close it, so I'm going to go to C. And then you're going to write the order. So I would write, they're usually going to tell you which letter. They always start with A, but you close the circuit and then you make a circuit, then write the sequence. So in this case, I can either go A, D, B, C, back to A, or you could go A, C, B, D, back to A. Either one will give it to you correctly. So when I do example 11, I like to do this a little bit different, mainly for the fact that you guys you can't really write on your computer. And so what I usually do is I will just, on my piece of paper, like on my scratch paper, I will just write down where my letters are. So I've got C, F, BE, and AD. So I write down a picture of what it looks like, and then I do that connection. So I look on my graph and I look to see, or on my mapping, whatever you want to call it, I look for my smallest number. So my smallest number is 2, which connects A and D. And then I look at the next smallest number up there, which is 5. And 5 connects C and D. And now that I've done that, I've got 2 lines coming off of D. I can't go to D anymore. D's already has 2 lines coming off of it. My next smallest number up there is, looks like 7. And that's connecting B and F. And so I just connect it. And then my next smallest number is 8. But because 8 is coming off of D and D is done, I can't use that number. So then I look for the next smallest number, which is 10. And that's going to connect A and F. So now A is done and F is done because you have 2 lines coming off of it. And you should notice that the only place that hasn't been visited is E. So both of these lines have to go back to E. And so now B has 2 lines coming off of it, C does, and so does E. So now when it asks you to write it, it's going to say write it starting and ending with vertex A. But I couldn't do that until I created the circuit. So once I've created the circuit, now you can write it as A to F to B to E to C to D back to A. Or you could have gone the other way. So you can go A, D, C, E, B, F back to A. And again, it doesn't matter. You just have to start with the vertex that they tell you to, but create your circuit first. The last thing that we're going to talk about is a spanning tree. A spanning tree is a path, so it's not a circuit. It's connecting all the points, so it needs to be connected, but it's not creating a circuit, and you need to be able to visit every point once. So these are all examples of spanning trees. So notice how unique they are. They're all different. They're not all going to create, well, they cannot create a circuit. And the nice thing about a spanning tree is that you still are doing the same thing. You're going shortest distance, shortest distance, shortest distance until you've visited everybody without creating a circuit. You can have as many lines coming off of a point. And so a spanning tree is kind of our easiest one to use. So I think this is not supposed to be, say, Krugel. Maybe it's Krugel. I thought it was Kruskal, but I think this is not Krugel. I think it's Kruskal. Anyway, I think. I should probably look that up really quick. So anyways, the minimum cost spanning tree. If we look at this example, it talks about a company. It's requiring a reliable internet and phone connectivity between 5 offices. And so they named them A, B, C, D, E. And they want to figure out the cheapest way to connect those company or those office buildings. Okay, and so they don't need to find a circuit or a path. They just want to make a call from one office to another and have it be the cheapest. And so the easiest way to do this is, again, I just put my points down. Again, because I can't write on my computer screen, it's easiest to just write down the general points, the vertices, and then create what you need to create. And so in this case, we are going to go the cheapest path. So as you look, our cheapest value or smallest number up there is 4, which is connecting A and B. Oh, pretend it hits. The next smallest number is 5, which connects A and E. The next smallest number is 6, but I can't do 6 because that makes a circuit, and we can't have a circuit. So the next smallest number is 7, which connects D and C. And then our next smallest number is 8, which connects A and C. And so now that is my spanning tree. So I visited every point only once, and it's connected. And that's the definition of using a spanning tree. So I can do the same thing with example 13. This time you have 6 points. And again, you can read through what they're doing. But the main idea here is if it says a spanning tree, we do not want to circuit. And we still do shortest until we visit everybody. So as we look at this one, we look at our smallest number up here, which is 2, which is going to connect. Whoops, I should have circled it, not crossed it off. So 2 connects, it looks like D and E. So D and E, it depends. You want to be careful. Pay attention to what it's asking you. In this case, it says the cost in thousands of dollars is in the table below. It says, how can they minimize the cost of new lines to lay? Now, if it says what is the cost going to be, then keep track of your values. In this case, it doesn't. It just says, how can they minimize the cost, not how much would it save them. So we've got 2. Our next smallest number is 4. So that's doing E and C. The next smallest number is 5. And that connects C and D, and that would make a circuit. So that one didn't work for us. The next smallest number is, it looks like 7, which is connecting C and B. So we're good there. And then we have 8, and that connects F and E. So we're still okay there. And then our next smallest number is 9, which is C and F. And that would create a circuit. So we're not okay with that one. And then our next smallest number is 14, which connects E and A. And then we visited everybody. And so there's our spanning tree. And so again, if it asks us for cost, we would add those values together. But if it doesn't, then they will ask you which segments would you use. And you're just going to say F, E, A, E, B, C, C, E, D, E. So they'll give you a list of all the possible vertices, and you just mark the ones that you would want. That's it for module 4. Like I said, repeated nearest neighbor is the hardest. And I can go through that with you if you want, but try to follow the numbers. That just takes forever to do. And it's just doing nearest neighbor as many times as you have vertices, and then figuring out the cost. So let me know if you need some help. Thanks. Sorry. Stop.